All right, today we're going to talk about magnetism, not animal magnetism, or someone has a magnetic personality, but magnetism as a force. Okay, magnets first discovered in a town called, or a region called Magnesia in Greece. You may recognize Magnesia as Philip of Magnesia, but more importantly, as a source of different compounds that contain the element that became known as magnesium because it was found here, and that's where the Phillips magnesia comes from. It contains some magnesium compounds in it that help to calm your stomach and coat your stomach. But in this region, according to legend, there was a shepherd named Magnus, and he dug up a rock that basically was attracted to iron and other things. It behaved very strangely, probably considered somewhat magical or mystical at the time. And eventually, this element, this rock, mineral became known as magnetite. And magnetite is a naturally occurring substance that is magnetic. And so they did not call it magnetite at the time. They called them lodestones. Lodestone meaning leading stone because they would point in certain directions. Slivers of lodestones could be placed upon water. And the Chinese first used this for navigation back in the 1100s, 12th century. And they realized that they could float it, it would always point a certain direction, and that would enable them to make basically the first compass. Okay, and compasses were very effective because of the magnet. Now, other than compasses, most of us think, there's not a whole lot of use for magnets. They're kind of neat, they're fun, and they do hold cabinets shut and things like that. But what really is the major purpose compared to like electricity? We would think of magnetism probably as a lesser less valuable type of thing. But as we will point out shortly, much of our civilization is based upon something having to do with magnets. So they are actually very important to us. Now, some of the main characteristics of a magnet we're fairly familiar with. And magnetism shares a lot in common with electricity. We've mentioned how circuit breakers, if too much current or electricity runs through electrical current, it will create a magnetic field which flips it off. Okay, and so in some ways magnets and magnetic forces are very similar to electric forces. In electricity we had positive and negative. In a magnet we have two poles we call the north and south. Okay, now there's not any difference between the north and the south other than they are opposites to each other. We could have called this one north and that one south, and it really doesn't matter. It's just that they're opposing forces, so there are opposing ones. Now, like electricity, magnets can be used to attract. If you put opposite ends of a magnet together, okay, like here's north and south, they will create a magnetic field between them. They would be attracted toward each other. South and north here are going to be attracted to each other. Opposites attract. And over here, if you put like poles together, north and north, they will repel each other. South and south will also repel each other. And so, just like electricity, you have two types of charges or forces acting, if you will, and they can be attracted or repelled to each other. And just like magnets or electricity, magnets, if you have the same pole, they will repel each other. If you have opposite poles, they are attracted. So in some ways very similar to electricity. All right. Also, like electricity, they don't have to touch an object to affect it. You can affect it from a distance. Magnets extend a field, as you can see here represented by the iron filings. You can see as you get farther and farther away, they get more spread out and it's weaker, but you have a magnetic field around it. And same thing here. You can see the magnetic field. So it can extend its influence out around it. Okay. And basically the force, how much force there is in this magnetic field, depends on the distance between the magnets. Once again, just like gravity and electricity, the amount of force exerted by the magnet depends on the distance between the two magnets. And as they get farther apart, then it changes drastically. Okay, and once again, we'll see a formula here. This is not the exact formula for the force of magnetism. It gets very complicated. But basically, the force of the magnet is proportional to the strength of the two poles, pole 1 and pole 2, the two magnets that are near each other, okay, divided by this distance squared. So once again, distance inverse square law kicks in, and as the distance increases, the force of magnetism decreases greatly, just like in gravity and electricity also. Okay. Now, how is it different than electricity? Well, first of all, magnetic forces are created by magnetic poles. Okay, we talk about the North Pole, or sometimes we say the north seeking. It's attracted toward, on Earth we'd say the direction north, which is toward the North Pole. South is the south seeking, and it points toward the South Pole. Okay. Now, when we talk about the North Pole of a magnet, okay, it is attracted to the opposite pole. So it's ironic that the north end of the magnet basically is attracted by an opposite force. So you could argue that the North Pole actually has a south attraction because opposites attract. So if this end is attracted toward the north, it's really the south, but we won't get into that. Okay, we'll say the north seeking end. This is not really the north end of a magnet. That's why it's called the north seeking. It will point toward the north and pull in the same direction as the North Pole. Earth's magnetic field at the North Pole. So, okay, and like I said, these poles will, if they're the same type of pole, they will repel each other. If they are opposites, they will attract. Okay, and the magnetic poles cannot be separated. They always come in pairs. You cannot have a one-pole magnet. Okay, so for example, if you were to take one magnet and break it in half, you would not have a magnet with a north and another magnet with a south pole. When you break it in half, there will be a north pole, and the other end of this little piece will be the south pole. This end will still be the south pole, but the end here where it broke would become the north pole. Okay, so basically magnets have two poles, and no matter how you break them, how many times, there's still going to be a north, south pole, north and south pole, north and south pole. Okay, they must have two poles. All right. Now, the area around a magnet is the magnetic field, and this is just an area that is influenced by the magnetic force, and you can see it extends out for a ways around the magnet. Eventually you get to a point out here where there would be no effect of it, so you're outside the magnetic field. All right, but the magnetic field is just the area that's influenced by the magnetic forces of that particular magnet. Now, the direction we say flows from, just like about electricity flowing from negative to positive, magnetism, the force flows from north to south. Okay. Now, the closer together the lines of this force field are, then it is considered, like here you see very close lines, so it's considered a very strong force field. The farther apart they are, where they spread out over here, you can kind of see, then that's considered to be a weaker field. So basically, when the lines are close together, the field is stronger. When the lines are farther apart, then we say that it is a weaker magnetic field. The question is, where does magnetism come from? What causes it? And basically, it comes down to an atomic thing. It occurs in the atom. Now, of course, obviously, enough atoms make together to make a bigger piece of the magnet, but it's on the atomic level, what causes a magnetic field has to do with the motion of the negative charges. Okay, and so if you remember our atom, we have a nucleus in the middle, all right, and it would have what type of charges? It would have protons that are positive and neutrons that are neutral. But around it, you would have electrons. But as the electrons go around, they spin. Okay, around, around, and around, they spin. And this is what we're going to find over and over again. Electricity and magnetism are like twins. When one's around, the other one will show up. Okay, and what happens is, as this electric charge, the negative charge electron, spins, it's moving. A moving electrical charge causes a magnetic field to exist. Okay, and so you have this, as it spins this direction, the magnetic field exists in this direction, north pole this direction and south pole this direction. Okay, now someone says, well, why isn't everything magnetic then? Because everything has electrons. Well, in a lot of things we have a balancing electron. Okay, and it may spin the opposite direction. Can't draw that very well, but spin the opposite direction, and therefore it creates a field going in the opposite direction with north down here, south up here, And so this will cancel out. So when you have electrons with opposite spins, they cancel each other out. And normally you get one electron spinning, then the next electron will spin in the opposite direction. And so if you have opposite spins, then it cancels out, and there is no magnetic field. But so they're spinning in reverse the direction of this one, and that just cancels it. All right. But if you have atoms that do not have enough electrons to cancel out those electrons, just based on the way their number of electrons that they have, all right, then those are your elements that are going to be good for making magnets. And it just happens that most magnets are made out of iron, Fe, which is a symbol for iron, alloy, some kind of iron alloy, which just means iron plus some other metal. And the other metal might be aluminum, it might be nickel, or it might be cobalt. Okay, these are the most common ones, or at least were the most common ones for a long time. Okay, and these are called, not surprisingly then, alnico magnets. That's just putting the elements aluminum, nickel, and cobalt together. They're symbols. Alnico magnets are just magnets that use these and are alloyed with iron, mixed with iron, to make magnets. So iron is the basic ingredient of most magnets, and then you add these elements to it. Okay, and the reason these are useful is because these are metals or elements that have uncanceled electrons. Therefore, they are more likely to have a magnetic charge. Okay, if you had a lot of the other elements have most of their electrons cancel each other out, so they have very weak or not very good ones. All right. Now, I should say that even though these are the most common ones, in past times, neodymium, which is a rare earth element, which is down at the bottom of the periodic table, and there are some other ones, but neodymium is the one most common. They are make very, very strong magnets. And you see some very small magnets that are very, very strong. We'll look at some in class, but basically neodymium magnets are the ones that we sometimes are called super magnets because they're very, very strong magnets. Okay, but most of the other magnets you'll see are made out of these. All right, now that is on the atomic level. You have these atoms spinning, but as you get in a bigger piece of metal, you might have different atoms that are pointing in different directions. And so basically what we would say that something that's magnetic or not, if we're looking at something magnetic or not, we would look at it's what we call domains. Okay, and a domain would just be an area within, say, a piece of metal. All right, and so within these domains you might have millions of atoms. Okay, so all these little tiny magnetic forces that we saw over here, you might have millions of them in each of these domains. Okay, and so they're adding up to a stronger force. But if this domain is not lined up in the same direction as the other domains in the material, it will still not be magnetic. So, for example, most pieces of iron by itself are not magnetic. Okay, but in a material that is magnetic, all of these fields have been lined up in the same direction. All these domains have all been pulled in the same direction. So, for example, if you were to take a magnet and stroke a piece of iron with it repeatedly, as you stroke it with that one pole of the magnet, it would line up all these different domains within the metal, and they would all point in the same direction, which would cause the piece of iron to become slightly magnetic. And you've probably maybe been using a screwdriver. I have a screwdriver that's been sitting in next to a magnet long enough in a drawer. It may become slightly magnetic. Okay, it's not a strong magnet, but it will become magnetic because all of the domains, the magnetic domains, these little areas in here, are all lined up in the same direction. So by stroking a piece of iron with a magnet, you could line up these domains. Sometimes tapping the magnet will help line these up. Dropping the magnet, which tends to point these all in opposite, can undo or weaken a magnet. Also, sometimes if it's heated up to a certain point, it's called the Curie point. But if it's to Curie point, it will cause it to destroy the magnetic properties. Iron is already, because of the spin of its electrons, it's already kind of a weak magnet to begin with, and so it's easily influenced and lined up the domains. That's why it makes such a good magnet. All right. We'll see you next time, and we'll talk about current.